Hypergeometric distribution. If a population contains capital N items, of which capital K are successes, and let's see, and little n items are picked without replacement, then the probability of picking n successes, not n successes, but x successes is f of x equals, so you are picking x successes from a total of capital K successes available. So the number of ways to do that is kcx. And if there are K successes in the capital N items, then there are n minus K non-successes or n minus K failures. And picking x successes, remember, you're picking a total of n items. So if x of them are successes, then n minus x of them are failures. So what we are saying here is kcx is the number of ways in which x successes are selected from K, and if x of them are successes, then automatically little n minus x are the failures. And so the n minus K is the total number of failures available. So what we are saying here is the number of ways of picking x successes out of K times the number of ways picking n minus x failures out of n minus K failures. So that's the number of ways in which we are picking x successes. So even though the picking of only the successes is mentioned, but picking x successes automatically implies that you're also picking up n minus x failures because you're picking a total of n items. And you know, n means multiplication. So this is the number of ways to pick successes, and this is the number of ways to pick failures. And to get the probability of this, of picking x successes, you'll divide it by the total number of ways in which the pickings can be done. So we are picking little n items out of capital N items. So the total number of possible ways of picking items, n items out of n, regardless of what they may be, is NCN. So same idea, probability of any event is obtained by always dividing by the total. And so in this case, the total possibilities are big N combination little n, because that's the number of ways in which you can pick little n items out of big N items, no matter what they might be. Okay, so now let's apply it here. A homeowner has 7 bulbs selected at random from a box containing 6 tulip bulbs and 7 daffodil bulbs. So the total bulbs are 7 plus 6 equals 13. So here the big N is 13. What's the probability homeowner planted 3 daffodil and 4 tulip? So now you can call any of them as successes. So let's say that daffodils are successes. So you would say that little n is equal to the number of daffodils available. So that is 7, and the tulips are 6. Okay, and the little n is the number of total picks. So you are talking about picking 3 daffodil bulbs and 4 tulip bulbs. So little n is 7, but not because of 7 daffodils, but because we are picking 3 daffodils and 4 tulips. So we're picking a total of 7, and little n is the total number of picks. And K is the successes, and if you call daffodils as successes, then K would be 7. Or you could, just to differentiate, let's say tulips are successes. So K is equal to 6. As I said, you can call any of them as successes as long as you're consistent during the problem. So because we are calling, let's call tulips as successes. So then K would be 6 in this problem. And X is the number of successes. So the number of tulip bulbs we are talking about is 4, 3 daffodils and 4 tulip bulbs. So X is equal to 4. So therefore, f of x would be K combination X, so 6 combination X. That's the way you pick 4 tulip bulbs out of 6 tulips available, and times, and then n minus K would be the daffodils available, which would be 13 minus 6, which is 7. And n minus X is how many daffodils you pick. So you're picking 3 daffodils. So although we have this nice formula, but a quick way of thinking on the fly is this is, you have the number of ways of picking the tulips. So there are 6 tulips available, and there are 4 tulips being picked. So there are 6 combination 4 ways of picking the 4 tulips. And similarly, 7 daffodils are available, and you're picking 3 daffodils. So there are 7 combination 3 ways of picking the daffodils. And you divide it by the total number of ways you can pick the 7 items from 13. So that's 13 combination 7. And you note that this number 13 is the sum of the 6 and the 7. And this 7 is the sum of this 4 and this 3. And that's always going to be the case, the way the hypergeometric distribution is set up. And let's see, that 6 combination 4 is 15, and times 7 combination 3, 7 combination 3. So I get 525 in the numerator, and divided by 13 combination 7. 0.3059 is what I get. 0.3059. Okay. So let's look at this one. From a lot of 13 missiles, 5 are selected at random and fired. Suppose the lot contains 4 defective missiles that will not fire. So in this case, the big N is, let's open a new file. So in this case, the big N is 13. Okay, so let's say firing is a success. So the number of successes available is the number of missiles that fire. And lot contains 4 defective. So 4 defective means there are 9 that are not defective. So K would be 9. Right, there are total 13, and of which 4 are defective. It means there are 9 which will fire and which are not defective. And let's see, you are picking little n. So in part A, well, okay, for both parts, you are picking 5. So 5 missiles are selected, and that applies to both parts A and B. So n, little n is the number of picks. That would be 5. And then in part A, we have to find f of 5. 5 missiles fire. So firing missiles, there are 9 firing missiles available, which means there are 9 which are going to work. So you want to select 5. You want to find the probability that all 5 fire. So you're picking 5, 5 are selected, and you find the probability that all 5 fire. So there are 9 good ones available. The number of ways to pick 5 out of them are 9 combination 5. And if uh, 5, all 5 fire, then there is none which is not going to fire, and the number of the defective ones are 4. So you're not picking any defectives. That's 4 combination 0, and then the total ways to pick 5 missiles out of 13 is 13 combination 5. So remember, this 5 on the top is the 5 successes, because in part A, you want all 5 to be successes. And this 5 in the bottom is the 5 total that we are picking. This is the 5 selected. So let's see, 9 combination 5 divided by 13 combination 5. 9 combination 5 divided by 13 combination 5. 0.0979. And then they say probability at most 2 will not fire. So probability at most 2 will not fire. So at most 2 means 0, 1, or 2 will not fire. Probability 0 not fire plus probability 1 not fire plus probability 2 not fire. So 0 not fire means all the 5 that you pick fire, and that's the probability we had in part A. So that's 0.0979 plus 1 not firing means that so you're picking a total of 5. So 1 not firing means 4 are going to fire. So 4 out of the 9 firing ones. You pick 4 firing ones out of the 9 firing ones, and 1 not fire. The numbers that don't fire is 4, and you're picking 1 out of those. And we divide that by 13C5. And the probability of 2 not firing means 3 firing. So 3 firing ones out of the 9 firing ones times 2 not firing ones out of the 4 not firing ones divided by 13C5 again. Okay. So probability none of them does not fire. It means all of them fire, that we already have. And then 1 not fire is the same as 4 firing. So 4 firing is 9C4 because there are 9 firing ones and there are 4 non-firing ones. So you select 1 out of those, and similarly here. So let's calculate it now. So 4C1 is 4 times 9C4. So 9 combination 4 is 126 times 4 divided by 13 combination 5. That's 0.3916. Okay, and then plus 4 combination 2 is 6 times 9 combination 3. divided by 13 combination 5. Okay, and then you add on the 0.0979. So I get 0.8811.